Hi folks, this is lecture 5 of maybe 5,
Dude.
because we were wondering what the so many was, and I'm thinking maybe it's 5, so we'll see. Maybe it's 6, maybe it's 5. On acids and bases, and this one is all about buffers, all the way down buffers, is this whole page, and problems, etc. And the question begins, which is, what is a buffer?
What's a buffer?
What's a buffer? A buffer.
A buffer is a solution that is able to resist changes in pH. When you throw acid in, it's like, I can handle this. When you throw base in, it's like, I can handle this. Whereas normally, if you just had water and you threw in some hydrochloric acid, it would go, whoa, my pH is 1! When you've got a buffered system, you throw in a little bit of hydrochloric acid, it's like, yeah, you just changed my hundredths place of my pH, but otherwise I'm fine. And that's really a good thing for things that need to maintain homeostasis, like us and living things.
Living things are buffers?
No, living things use buffers to maintain their pH. And the real famous one is blood. And blood has got a pH of 7.41. And if you put a little bit too much acid in your blood, the blood can handle it. And if you put a little bit too much base in your blood, the blood can handle it without your blood suddenly becoming pH 1, which would kill you immediately,
Yes.
which is good. So living systems need to be able to maintain the pH to be relatively constant, and a buffer is the way that that's done. So we're going to talk about how buffers do that and how one can make a buffered system in the lab so that you can do stuff in lab in buffers without the pH going insane. So here's how you make them. You dissolve a weak acid and its conjugate base salt, or a weak base and its conjugate acid salt, which is what we just did up here in this last lecture, part C. A mixture that is 0.1 molar in propanoic acid and 0.1 molar in sodium propanoate. This is a weak acid and its basic conjugate base salt. And what you see is that if you've got a little bit of the acid in there, if you throw in base, it'll react and kind of mess with the equilibrium system a little bit. If you throw in acid, it'll react with the base and shift the equilibrium system a little bit. But you still have nearly the same amounts of weak acid and weak base. They just kind of flow back and forth a little bit instead of going bam, 100% dissociation like you get with strong acid and strong base. So it kind of eats the strong acid and base that you put into the system and maintains a weak acid, weak base situation. So for example, if you've got this guy here, you've got a solution that's got 1 molar hydrofluoric acid, which if you remember, hydrofluoric acid is a weak acid, and 1 molar sodium fluoride. This is an example of the common ion thing, where you've got fluoride and fluoride. You're putting in the weak acid and its conjugate base. The sodium doesn't matter, if you remember, because it's an ion from the strong base, sodium hydroxide. Strong things don't affect pH, weak things do. So this hydrofluoric acid is making it sort of slightly acidic, this fluoride is making it slightly basic, and it'll equilibrate to a pH, and whether it's acidic or basic depends on whether the Ka is stronger or the Kb is stronger. So here's our equilibrium for this situation, HF, back and forth, your loose protons and your fluoride. Here's the acid side, here's the base side, okay? So what would happen to the equilibrium if we added some potassium hydroxide? The potassium hydroxide is a strong base, and strong bases react with acids. So hydrofluoric acid is your acid. It's going to react with some of your hydrofluoric acid, and as long as there's more hydrofluoric acid than potassium hydroxide, what you'll end up with at the end is some hydrofluoric acid and some fluoride. All the strong base is gone. It got reacted away. So what is this? The hydroxide would react with some of this acid, and then you're pulling away some of the reactant. And if you remember Le Chatelier's principle, you pull away some of the reactant and the products will shift the thing back left. And so this equilibrium kind of insistently stays present even though you're throwing strong base at it. If you did the opposite and you threw some hydrochloric acid onto this buffered system here, that acid would react with this base, the fluoride, and it would pull out some of that fluoride and react and form, it would form water and salt of some kind. And then, well, you've messed with this equilibrium, you've pulled away some of the product, and the reactant would shift to the right to fix that equilibrium. So it kind of just flows back and forth and handles anything that you throw at it, as long as you don't use up all of it. And so we'll get to that. That's called the buffering capacity. If you don't use up all of it, it's just going to stay at kind of a nice centralized pH. It goes up a little bit, it goes down a little bit, but it doesn't go boom 12, which is alarming. That's bad. So let's do an example problem of a buffered solution, and we already know how to do all this. This won't be so hard. The math is the same until it gets easier. It's about to get easier. I know, right? Yay! The math is going to get easier in just 1 minute. So let's flip over to the black screen. What is the initial pH of the buffered solution in the previous box? That's this buffered solution. I'm doing this right? I think I'm doing this right. All right. So it's the buffered solution in that previous box is 0.1 molar or 1 molar?
1 molar.
1 molar. Okay. 1 molar. Do you like how I did that? None of this, and 1 molar of fluoride from sodium fluoride minus X plus X. We've already done this. Yeah, I know. I told you. 1 minus X, X, 1 plus X. There's your Ka. So 7.2 e to the negative 4 equals X. Do you know what's going to happen yet? I hope you recognize it.
X is going to equal the Ka.
Yep, X is going to equal the Ka. Because your X's die. X is less than 5%. Am I going to remember? Probably not. The 1's cancel. X equals the Ka, so negative log of the Ka is the pH, and I have it written down somewhere. It ends up being, whoa, dude, 3.14. Just kidding. It's pi. It's not actually pi, but it looks like pi. Anyway, X equals less than 5%. I remembered. 7.2 e to the negative 4 over 0.1. I know. Over 1 times 100 is 0.7%. I think. I didn't do it on my paper.
Remember, it's 1, not 0.1.
Yeah, it is 1. I'm not going to divide by 1. I'm just not. Yeah, 0.07. It's 0.07%. We'll be fine. We're good. So our pH is 3.14, and that's of this buffered solution. So it looks to me, yeah. So you can see this. It's an acidic pH, and this is a buffered solution. So you've got some acid and its conjugate base present. So you sort of wonder, well, is it going to be acidic or basic? Depends on whether the Ka or the Kb is stronger. And this is a pretty strong Ka, e to the negative 4. This is going to make this one something e to the negative 10. So he's kind of a sissy compared to hydrofluoric acid. So there you go. That's how you do these. Now, the much easier method of calculating a buffer pH.
Ooh, I like the sound of this.
Are you ready? Are you ready?
I so
okay.
like the sound of
It's
this.
called, well, the name is worse.
Oh.
It's called the Henderson-Hasselbalch Equation. I know, right?
That's a mouthful.
Hasselbalch. The Henderson-Hasselbalch equation is like this. The pH of your buffered solution is equal to your pKa plus the log of the concentration of your base divided by the concentration of your acid. And I call this logba. Okay? pKa plus logba. And if you look, one thing that you have to remember is that log of 1 is 0. Because 10 to the 0th power is 1. Because anything to the 0th power is 1. So what you end up with is, well, what's my pH? It's my pKa, which in this case is pi, plus logba, which base over acid is 1 over 1. So that's log of 1. So when you have log of 1, this part ends up being 0. So when you have a buffered system where the acid part and the base part are equal in proportions, the pH is the pKa.
Very nice.
So that's that. Look at how much less. This is less math.
Woohoo!
Less math, more math, and you can do it. You can do it the long way. And so if you forget about the Henderson-Hasselbalch equation, go ahead, do it the long way. You might run out of time.
Oh.
And also, I always forget to use the Henderson-Hasselbalch equation. Like, I'm so bad about it. I'll just sit and do this, like, really long ice. No. It's like, oh, dang it. So anyway, don't be like me. Don't do that. The Henderson-Hasselbalch equation. Da-da-da-da. Why do I always forget? Okay, so some things to know about buffers. You need to sort of understand them. And here are several bullet points of understanding. We've talked about this. They're made of the weak acid and their corresponding weak base, so they're conjugate weak base. And the way that they write these as kind of a general idea is ha and ah, or b and bh, which is kind of as follows. Let's scroll over here. It looks beautiful. Here you've got H attached to, this is the acid. That's A is not an element, right? They're just saying, some weak acid thing. And then later it separates into the H plus and the A minus, which ironically in this situation, it's a base. So, ha! Or you could have a situation which is more like ammonia, where you've got the ammonium form and it separates into its base form and H plus, which they represent as BH and B and H. Okay, so it can either be the regular way, like hydrogen fluoride, hydrofluoric acid, or if you have an ammonium sort of system, they'll use the B to represent that. That doesn't come up as much. But so don't freak out, I guess the point is when you see ha, I don't know what element A is. They just mean, some weak acid. When your H plus is added to your buffer system, it reacts with your base and forms more acid. If you're adding it to your buffer system and your buffer system is the B version, it reacts with your base and forms more acid. Okay. When hydroxide is added to your buffer system, it reacts with the acid. We talked about this up here. I can't just point. Up here. We talked about this up here, what would happen with these two situations. But when you add hydroxide to a buffered system, the hydroxide reacts with the acid, and you end up with some water and more base, or some water and some more base. And after that reaction has occurred, the equilibrium will reassert itself and kind of rebalance. So that's what happens when you add acid or base to a buffered system. If you add acid or base to water, it dissociates 100% and just totally shoots your pH out the roof, either up or down. If you add acid, it makes it really acidic all of a sudden. If you add base, it makes it really basic all of a sudden.
Even a weak acid? Or a weak base?
Even a weak acid or a weak base? Yeah, it will set it, it will move that pH 3 or 4 points if it's a weak acid or a weak base. It will move that pH 7 or 8 points if it's a strong base or strong acid. And, that's not something that you want in your blood.
No.
You're a doctor. What is an alarming blood pH?
An acidic alarming blood pH would be like 7.2.
7.2.
7.2, 7.1. If it goes below 6.8, you're probably dead.
If it goes below 6.8, you're probably dead?
Yeah.
That's not very far. Like, that's not...
very little.
That's not even a whole point of pH. So you don't want to die.
Generally,
that's one of the goals
in life.
In life.
It's a good goal to have in life.
People that don't have that goal don't have goals.
life.
I know, right? So that's a good thing to keep in mind, is that, in a buffered system, you don't want it to move a whole point.
Ooh,
You don't want it, you don't really want it to move a tenth of a point.
no,
No.
no.
When you start to feel bad.
You start to feel bad when it moves like a tenth of a point. You're feeling it.
All
Your
right.
body is noticing it. You don't feel good.
You don't feel good when it
And
moves
you-
a tenth of a point.
You're often in the hospital if it moves more than that.
Hospital if it moves more than a tenth of a point. This is great. This is very, very interesting, alarming. I don't know what it is. Okay. So the pH that you do have is determined by the ratio of the concentrations of the weak acid to the weak base, which is a long sentence to mean, look at this here. This is important. How much HF and how much F you've got. And it's the ratio, it's not the overall values. You end up with a pH of 3.14 when these are equal. So this could be 2 and 2, or 10 and 10, or 0.1 and 0.1, or 0.01 and 0.01, and you still end up with a pH of 3.14. It's not their total value, it's their ratio. Now, getting to the next thing is called the buffering capacity. If you have only got 0.01 molar HF and 0.01 molar fluoride, you're going to use up all of it. It's going to get all neutralized pretty rapidly. And so your buffering system is a buffering system for all of 5 minutes. And then you kind of blow it out and you don't have a buffering system anymore. So it's a buffering system as long as there is some remaining hydrofluoric acid and fluoride. And so one of the things that's important when, for example, in the lab, you're thinking, now, how shall I make my buffered system in order to make it be resilient? You want to have pretty close to a 1-to-1 ratio, and you want to have a 1-to-1 ratio where the ratio is using large numbers. So instead of 0.1 to 0.1, 10 to 10. It's going to take a long time to react all of the 10 molar compared to if you only had 0.1 molar. And that's called the buffering capacity. Its capacity to survive being attacked when it is the buffering system by kind of insults from the environment. People wandering by, pouring hydrochloric acid in there, or drinking too much orange juice or something. What are some things that can affect our pH in our blood?
If you have diabetes and you have diabetic ketoacidosis.
If you have diabetes, okay. Let's say I wanted to go and affect my blood pH today. What should I do?
Drink a lot of alcohol.
Drink a lot of alcohol?
Yeah.
What would that do?
That makes you acidic.
It makes me acidic.
Eventually, it'll overcome your buffering system.
Wow. Is that a reason to end up in the hospital and die of too much alcoholing?
It can be.
Wow.
Yeah.
I didn't know that.
It can make you quite sick.
Well, I don't recommend that to our readers. Dear readers. It's determined by the ratio. The pH is determined by the ratio, but it's also important to have large numbers in order to have a good buffering capacity. It is a good idea to keep that ratio near 1 because when you have a ratio near 1, it can, for example, in this situation where the ratio is 1, this buffering system can withstand attack by base by using up the acid, and it can withstand attack by acid by using up the base. If it were a situation of like 1 molar and 0.1 molar, it could withstand quite a lot of attack by base, but not nearly any attack by acid, because you would end up using up all of this and then bam, you're toasted. So it's a good idea to keep the ratio about 1 so that you can handle anything that's thrown at you, basically. Now, sometimes you know that you're only going to be dealing with insults from the environment that are acidic. Like, well, I need this to be a buffer, but generally the thing that happens is that somebody throws acid in, and so I'm going to want to have a buffer that has more base to it. But if you don't really know, then you want to have both. A resilient buffering system has got some near equal amounts of both. Large buffering capacity has large concentrations, and if you're in the lab and you need to choose and make a buffer, you think of your Henderson-Hasselbalch equation, which is the pH equals pKa plus log BA. And the log BA, the log of 1 is 0. And it's a good idea to have the BA equal to 1. So that means that in general, if you're making the buffer well, the pH of the buffer is going to equal the pKa of the buffer materials. And so sometimes you're charged with, hey, would you go make a buffer with a pH of like 5 or something? And you go, okay, and you kind of go, well, what do you want me to make it of? Like, what chemicals should I use? And generally what you do is you go, okay, the pH of 5 is going to be easily made from something that has a pKa of 5 or a Ka of e to the negative 5. So if I want a buffer with a pH of 5, I should choose an acid with a Ka of something times e to the negative 5. And I should add that acid and its conjugate base, that's these two blanks, conjugate base salt in large concentrations. So you go pick out an acid, you find a bottle containing its salt as well, you mix those together in large concentrations, and then you kind of fiddle with it a little bit. You go, oh, it needs to be a little bit more acidic, I'll put a little bit more acid in there. Okay, there, I have a buffer. Here you go. And you say, thank you. No, don't drink my buffer. Okay, so there you are. And we're going to have a problem that asks you to make a buffer in a minute. So this example is going to show you the relevance of large concentrations and buffering capacity. So we're going to have the initial pH of the buffer, and then we're going to see what happens when you add hydrochloric acid to a 5 molar version of your buffer and to a 0.05 molar version of your buffer. It would be good if your buffer kind of lived to tell the tale. And if the buffer succumbs to the evil influence of the acid, then you know that it wasn't a really well-made buffer. So let us go and do that problem and see how it turns out for us. Do you know which one is going to be good? Do you suspect?
I haven't even looked at this yet.
You haven't even looked at the problem yet. Okay, well, here we go. Calculate the pH when 0.01 moles of gaseous hydrochloride is added to 1.0 liters of each of the following solutions. And the Ka, here I should probably scooch this over some. The Ka is 1.8 E negative 5 for acetic. You recognize that one? That one always comes up, doesn't it? For acetic acid. So here's our initial pH of the buffer. Now, I am tempted to go and do an ice chart, but this is a buffer. And so I can use the Henderson-Hasselbalch equation. So that's the pH. They're asking for the pH. So the pH is going to be equal to the pKa plus log BA. Okay, so the pH is, what is my pKa? Do you know how to do that? That's important.
It is the negative log of the Ka.
That is right. The pKa is the negative log of the Ka. So the pKa is negative log of 1.8 E negative 5, which, as it turns out, is some number that I have here, is 4.74, which should make sense because it should be around 5. Okay, so the pKa is 4.74 plus log of base over acid. What is the concentration of base and acid? It doesn't really say, but for B it's 5 to 5, and for C it's 0.05 and 0.05. So what is my ratio of BA going to be in both cases?
1 to 1.
Yeah, so 1 and 1. And what is the log of 1?
0.
0. So 4.74, that is our initial pH. So for this, when we start, before we add any hydrochloric acid, the pH is 4.74. And for this buffer as well, the pH is 4.74. Well, they must be exactly the same then. No, they are not exactly the same then. There's an important distinction. All right, so we are going to take this buffer and add some acid to it. So when we do that, we're going to have a reaction, and that's going to be a stoichiometric calculation. So that's going to be hydrochloric acid. If we pour hydrochloric acid in here, what is it going to react with?
It's going to react with the base.
The base. And which dude is the base?
The sodium acetate.
The sodium acetate. The acetate, actually, all by himself. Although we can include the sodium if we feel like it. Let's do that. It'll be prettier.
Yeah.
And that's going to make sodium chloride, nice salt there, and acetic acid. And that's going to be before the reaction. Remember, this is a reaction, not an equilibrium. This is a reaction when you are adding acid to a buffer or base to a buffer. And so it's a before and after chart.
Okay.
And the things that go in before and after charts are
Moles.
moles.
Not molarity.
Not molarity, moles. And that's crucial. All right, so it says 0.01 moles. So 0.01, that was nice. I gave that to you. I'm too nice. 1 liter of the following solutions. So in 1 liter of 5 molar, how many moles of this?
5 moles.
That's 5 moles. And there's none of this and none of this. What are we going to run out of first?
The hydrochloric acid.
The hydrochloric acid.
Most
That's going to be
definitely.
gone. That's going to be 0.01. That's 0.01. And what are we left with our sodium acetate?
4.99.
4.99 moles. And so what we have is this for our acetic acid. And actually, no, sorry. How much
Okay.
acetic acid? You were wondering. You're just sitting there wondering how much acetic acid is there at the beginning.
Is 5 molar.
Yeah.
So 5 moles.
5 moles.
Okay.
So that's
Makes more sense.
5.01. There we go.
There we go.
Now we can go and do the ice chart. No. We can go and do the Henderson-Hasselbalch equation, which goes like this. The pH at this point is going to be the pKa, which, by the way, is still 4.74, plus logba. Log of, how much base do we have now?
5.01 moles.
Base.
Base is 4.99 moles.
4.99. And how much acid do we have?
5.01 moles.
But that's almost 1, yeah. Guess how much this has changed the pH?
Almost nil.
Almost none. What do we have here? We have, oh, this is great. I want to see the decimals here, because that's where it's going to end up. It's 4.74 plus log of 4.99 divided by 5.01. That's 4.738,
Okay then.
which, considering how many sig figs we have, is 4.74. So, no difference. We just poured hydrochloric acid, and it didn't do anything.
That's called a buffer.
That's nice.
That
Thanks,
is nice.
thanks, buffer. You sure
welcome.
buffered that. All right, next. This one. What if we pour it on this guy? But that's the same thing. I don't know. Let's see if it is.
You're saying it like maybe it's not the same thing.
Shh.
Suspicious.
Yeah, all right. Hydrochloric acid. We're going to pour it on this buffer.
It's in front of my face.
Shh.
They like my face.
Uh-huh. Yeah. Is your face even in the camera? I
Probably
don't
not.
know. All right. Before and after and 0.01 and none of this and 0.05. Ooh, that's a small number. All right. So we still run out of hydrochloric acid first. We make 0.01 of this. We lose 0.01 of this to give us 0.04, and we gain 0.01 to give us 0.06 moles. So now we can go do our ice chart. No, it's a buffer. But we can do the ice chart, right? Yes, feel free. 4.74 plus log of, well, how much base do we have now?
0.04.
0.04 over 0.06. Hey, that's not 1. Yeah, you're right. It's not 1. You stick that in and you get the pH 4.56.
Ooh.
Ooh,
It changed it a little.
it did change it a little. So, but did it change it as much as it would have if there was no buffering?
No.
What would the pH be if there was no buffering? If we just threw 0.01 moles of hydrochloric acid into a liter of water, what would the pH be?
It would be like 1 or 2 or whatever the
How would I find out?
pKa.
No.
Because it's hydrochloric acid, so it's a strong acid and would dissociate completely.
It would dissociate completely, and so you do negative log of 0.01,
0.01.
which I believe is 2. Yep. We would have a pH of 2 if there were no buffering.
Wow.
We have a pH of 4.56 with some small buffering, but pretty reasonable buffering. And we don't even change the pH at all in our sig figs. And what you can see is that's because these numbers were big. And when those numbers are big, it's sort of hard to change the ratio of 1 to 1 to anything else. When the numbers are small, it's a little bit easier. We've just changed the ratio to 4/6. What here it's 499 to 501. Yeah, So that's why your buffering capacity is important, because the larger the buffering capacity, the smaller the changes when you do insult it with acids and bases from the environment. All right. Here we have a problem on the back. Calculate the pH of a solution that is 1 molar in nitrous acid and 1 molar in, what is that, sodium nitrite. Did you like that name? Nitrite. That's easy. I can go do an ice chart.
Well, no.
It's a buffer.
It's a buffer.
But it doesn't say that it's a buffer.
But it is a buffer. This is a weak acid, and this is its conjugate base.
Also, we're in the buffering section.
I know, right? So we need Henderson-Hasselbalch. Oh, yeah, also we are kind of on the buffering section. Log B. And the pKa, well, I don't know the Ka. You didn't give it to me. I did, actually. There's a chart down here. Hello, delicious chart.
Are we gonna like this chart?
Yeah, I hope you love charts. 4e to the negative 4 is the Ka for nitrous. So that's... and by the way, since it's 1 to 1, the log B is irrelevant. So it's just the pKa. So what should the pH be close to?
4.
It should be somewhere around 4. And it's actually 3.397. Bam. That was easy.
I miss my ice charts.
I know, me too.
There
All
we
right,
go.
calculate the new pH after 0.10 moles of sodium hydroxide has been added. Okay, well, now we get to do a stoichiometry calculation because we are doing a neutralization reaction.
Not equilibrium.
And sodium hydroxide is going to react with the acid part, right?
Right.
And make some water and sodium nitrite before and after. And we've got 0.1 moles, and this is... And it's important that it's 1 liter of the solution, by the way, because 1 molar, 1 liter, that's 1 mole. 0.1 moles, I don't care about water. 1 mole, 0.9, and 1.1. Yes?
Yes.
Yes. So now we can go do our ice chart.
No.
Now we can use the Henderson-Hasselbalch equation because it's a buffer.
It's a buffer because it has the acid and its conjugate base present. You can use that Henderson-Hasselbalch as long as they are both there. If you end up with a 0 in B or A, it kind of breaks math, so you can't do that. So the pH is 3.397 plus log of, which one is our base?
The sodium nitrite.
Yep, 1.1 over 0.9. Is this going to be significantly different?
No.
No, not really. And it gives us 3.49. Hey, buffer, buffer, buffer. Nice. Okay, calculate the new pH after 0.2 moles of hydrochloric acid is added to a liter of the original solution. Okay, you can figure out how to do this yourselves. Go do it. The answer, if you are right, is 3.22. Okay. 2. Which of the acids that left would be the best choice for making a pH 7 buffer? And tell me how to make 1 liter of this buffer. And by that I mean how many liters of each thing, how many moles of each thing should we put in? So a pH 7 buffer. A pH 7 buffer is, when you think about Henderson-Hasselbalch, you want this part to be 0. You want this part to be 0 for it to be good. Yeah. So in general, you want your pH to equal your pKa, which means that you want your, since this wants to be 7, you want your pKa to have your Ka to have the exponent near 7. So we kind of look at our list and we go, now which one is a reasonable dude with a -7? The best guy I see is Hypochlorous Acid. So okay, I guess I'll use him. He's not great, but this is the list of the acids I have in the cabinet, let's say. So we go, okay, so for hypochlorous acid, we've got pH equals pKa plus log B, and we want our pH to be 7, and our pKa is negative log of 3.5 e negative 8 plus log B. And now you can solve for B and A to figure out how much of each one you should put in there. So negative log of 3.5 e to the negative 8, that's 7.46. So it turns out that log of B needs to equal negative 0.46. And I need to scroll over again. I'm sort of out of room here. And so what that means is I need to unlog, and that's 10 to the, so I'll come up here, 10 to the negative 0.46 equals B. And so that means that 0.35 equals base over acid. That means that my ratio of base to acid ought to be 0.35. Well, what does that mean? It's sort of hard until you realize that it's very helpful to do this. That way you can say, all right, we can have 0.35 base and 1 acid. Ta-da!
Ratio.
It's a ratio, so you can make up anything you want as long as the ratio works. So you could do 0.7 and 2. You could do 3.5 and 10. You could do 35 and 100. I don't really care. Although 35 and 100 is maybe too many moles to fit into a liter. But this is pretty reasonable. Now, this has got more acid than base, which means that this buffering system is going to be able to handle more insults from bases than it will from acids. But you're going to have to live with that because hypochlorous acid is the one that you get to live with. So if you're worried about your buffering system not being resilient enough, you could up this to 3.5 and 10, for example, and then that guy is going to live a long time. So there you are. So you would put this number of moles in to a flask, say, and then you'd fill it up to 1 liter, dissolve, 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 dissolve. You have your buffer, and then you hand it to someone and say, here you go, and then they don't drink it. Ugh, you're terrible. Okay, that's it. Hey, that one's short, and that's the end. And there's only 5 lectures. I thought there were going to be 8. You should be happy. Goodbye.